we're going to take a moment to briefly discuss some things you can do with arc length and the arc length function. These are not things that we're going to focus on very heavily at all this semester. So just know that these things are there. Maybe take very, very light notes. I think the important thing here is not to expect any of these concepts to make it onto a quiz or exam, but rather just know that there are lots of things you can do, and in physics I suppose there are places where you may need to use some of these things. We're not going to be so concerned with all of these applications of arc length. Okay, so we treat things here very briefly. If you ever needed these sorts of things in a future math or physics or chemistry class or whatever, I think the thing to do would just be to look up what you need. Um, I think really the whole point of what we've said already today is to just um, get you still more comfortable with the idea that vector functions are parametrizations and vice versa, and that both are really just trying to describe the motion of a single object in space, like a little bug just moving around in 3D, and what things you can do with it. Right, so one thing you can do is you can parametrize a curve by its arc length. The thing is that you've perhaps seen some parametrizations where the point seems to be zipping around very quickly, and at other moments in time, the point does not move very far very quickly at all. And so what you could do is from this arc length function that we just saw, due to the fundamental theorem of calculus, you can note that the derivative of s should just be the integrand that's in here, so r prime of t. And then from the original vector function, you can compute s of t, and in the equation for s of t, solve for t in terms of s. That is, get t of s and then replace t in r of t with this new expression of t that's written in terms of s. This looks like a lot of things to say. Again, please don't overly stress about this. The whole point is just to take a cartoon approach to this. We'll look at a brief example in just a moment, but let's just talk about what this does. What is parametrizing a curve with respect to the arc length or by the arc length? What does this do? Imagine that r of t models the movement of a fly, where t is time. And maybe sometimes the fly is moving very fast, and other times the fly is moving slow. Think about the magnitude of r prime of t as being an instantaneous velocity, and maybe instead of this erratic nature where sometimes the fly is being very lazy and other times it's on caffeine, this new thing, this re-parametrization by arc length, it's the same path, but imagine that the fly has to be on cruise control. Okay, so what happens now is that there will be a new parameter s, that using this new parameter s, as s increases 1 unit at a time, the fly will end up traversing the same amount of arc length in that time frame. So this all sounds confusing. Again, the next example, don't look into it too much, right? Don't worry about trying to memorize a recipe here. I just wanted to show the recipe once. You're not going to be required to do it this semester. It just may be good to just see it once more than anything. So let's parameterize the vector function cosine of t, sine of t, t with respect to the arc length, starting at the point 1, 0, 0. Okay, so we compute the so take ds over dt, which is computed as the magnitude of the velocity vector. In this case, you're going to end up getting root 2, and we compute the arc length function from this. You got to go back to the slide to see that the setup of this is an integral from a starting t value. So you have to get this t equals 0 by recovering what value of t is going to create the point 1, 0, 0. And it's going to go up to t. So this arc length function is a function with respect to the input being the original parameter t. And if we do this integration as set up by the formula, in this case, copy this, import this root 2, and we're just integrating the constant root 2. with respect to a variable called u. So it'll be root 2 times u, but that's going to be evaluated where you plug in t for u and then plug in 0 for u and subtract. So you end up with t times root 2. And then from this, you should solve for t. And here we have it. So t is equal to s over root 2. So this s over root 2 is what the previous slide is referring to as t of s, right? That's how you write t in terms of s. Okay, so t as a function of s, you have t of s is equal to s over root 2. And now here's the re-parametrization. Really, you got to go back to what the previous slide said. Sorry for this, but it really is just literally taking the r of t in the beginning and composing. If you want to call it composing, you can call it that. It's r of t of s. If you don't like that, all that's really happening, and think about how you would explain function composition to somebody who's in college algebra, all you're really doing is everywhere you see a t, you're replacing the t with your formula for t in terms of s. And so here you have it. This one was real nice because the due to how the derivatives worked out for this example, s and t grow at a linear relate with respect to each other using root 2 as a constant of proportionality. There will be certainly examples where you can do this kind of procedure and the change between s and t is not so uniform, but let's not worry about all that because that's just adds a layer of complication that we really don't even need this re-parametrization with respect to arc length for this class, so we're not going to emphasize it. It's just I wanted you to see it once. Here's another thing that, again, let's not worry about. In fact, you'll see even fewer details. Curvature is something that you can compute from the arc length function. Curvature, which is usually denoted kappa, measures how curvy or like how wiggly or crooked a path is. It's computed like this. It itself is a function in that instantaneously at each moment you can have at each spot you can have for each value of t you'll have a constant, a scalar corresponding to the curvature at a specific point, and it is computed as the magnitude of the derivative of the unit tangent vector with respect to the arc length. Okay, that's, again, let's not worry about it. We're not going to use it. It's not going to show up later on in Calc 3. And then finally, one other thing that you can do is there's this thing called the Tnb frame. It's named this way for tangent, normal, and binormal. The point is, based on the arc length function, you can create 3 unit vectors. One is the tangent, so imagine you're moving along a curve, or a bug is moving along a curve in 3-dimensional space. And first, there's the unit vector that's in the direction that the bug is instantaneously traveling. That's the tangent vector. That's helpful. But then there's also, if you're in 3D space, at any specific point, if you draw a vector, there ought to be 2 other vectors that you can draw such that all 3 vectors are pairwise orthogonal to each other. Right? So it's sort of like at that specific moment, like you take a picture and you maybe have a speedometer attached to the bug, then you know, first of all, again, the tangent vector is the easy one, right? That's just a normal vector that where you let go of what the speedometer said, but you at least know what direction the bug is traveling. And at that point, it's almost like you want to create your new x, y, and z axes. And you really want everything real nice and perpendicular. So you create, in addition to the tangent vector, 2 more vectors. One's called the normal, one's called the binormal. Let's not get into it. But those 3 vectors create sort of like this sort of situation that may be super nice for computation. Specifically, you can momentarily imagine that the bug is located right at the origin. And maybe it's not, but maybe you create a new set of axes, right? Just temporarily, momentarily, the bug is the origin. It's like you have the original axes in black, and let's just say you have a new set of axes drawn in green or whatever. And the new axes that are drawn in green all intersect right at the new origin being the bug, and those 3 axes with the 90-degree angles between those 3 green axes, that's really awesome for some computations. Again, we don't use it. I've never used it in Calc 3. It's just a nice application. If you actually deal with motion in space, By space, I don't mean outer space. I just mean in three-dimensional space, this Tnb frame can be very helpful for computation. But we won't need it, so let's not get into the details of it.